So now we're going to talk about buffers. And the neat thing about buffers is that all a buffer is really a solution where you have a weak acid and its conjugate base, or a weak base and its conjugate acid. So if we take a look at our typical acid, which is HA, and we throw it into water, let's say, what's going to end up happening is on the other side, won't we end up with H3O plus, and we end up with A minus. This right here, this HA and this A minus, they would be a conjugate acid-base pair. And if you had a certain amount of HA and A minus together in a solution, we would call that a buffer. So one of the things that the buffers do that we'll learn about in a little bit is that buffers resist changes in their pH, which is something we're going to get to. And how we make buffers is also something we're going to get to. But one of the things we want to know is how do we figure out the pH of a buffer? And one of the things that you're going to notice almost immediately is that this problem that we're going to do right now, which is essentially taking 0.5 molar of the acetic acid, our original acid, and 0.5 molar of its conjugate base, is exactly like the problem we did with the common ion. So let's jump right into it. And if we are going to do acetic acid, which I don't want to write, I'm going to write it as HAC, right? We're going to throw that into water like we typically do. And when we throw it into water, we're going to end up with H3O plus, and we're going to end up with AC minus. Now, we always do ice problems when we're solving problems like this, so we're going to do an ice problem. Initially, don't we have 0.50 molar of the HAC? But then it also says we have 0.50 molar of sodium acetate. Again, I'm going to remind you what we did over previously. If I have NaC2H3O2, and I know that I have 0.50 molar of that, we don't care about the Na. It's a spectator ion. If you want to go even farther, this is a neutral producing thing. This is a base, a conjugate base. So what we do care about is that we have 0.50 molar C2H3O2 minus. And where does that fit into our overall equation here? Well, initially, we're going to have 0.50 molar of this. I've been kind of remiss in putting in the states of matter here, but these are aqueous, aqueous, and aqueous. That's just so you know that we never put H2O into a K expression or equilibrium expression or the law of mass action, whatever you prefer to call it. When we do our change, we're going to do the exact same thing we've done before. We're going to go minus X here, we're going to go plus X here, and we're going to go plus X here. And at equilibrium, we're going to have 0.50 minus X, X, and 0.50 plus X. Now, if we set up our K expression, our equilibrium expression, which I should have done before, we can solve this using Ka. And if we do it, we're going to end up with H3O plus on the top times AC minus all over HAC. Now, we happen to be given the Ka in this problem, which is 1.8 times 10 to the negative 5. Now, since we have this, we can plug our equilibrium values back into here because they're asking us to solve for the pH. And we know that if we're able to solve for our X value right here, that's our H3O plus, and we can take the negative log of that to figure out our pH. So we're going to plug everything back into our equation. So all these variables are going to go back into here, and we're going to have X, 0.50 plus X, and you're going to have 0.50 minus X down below. Now, again, we're going to end up with a very similar problem that we had before, because if you actually do the mathematics on this and we set it up, you're going to end up with X is X times 0.050, because this is going to be 5% ruled out, and this is going to be 5% ruled out. Why? Because this is a very small K value, and X leaving that very small amount of K is going to be almost negligible. So if we have that, I didn't want to put 0.05, it's actually 0.5 over 0.5. And again, do you guys see that since that's equal to 1.8 times 10 to the negative 5, do you see that that's going to be our X value times 10 to the negative 5, and our X value is not equal to our H3O plus value? Now, again, we've given you the really basic problems here, no pun intended, because we're giving you 0.5 and 0.5 as our original amounts. That's not always going to be the case, although to be fair, having the exact amount of acid and its conjugate base makes the best buffer. If I have 1.8 times 10 to the negative 5, and I go pH is equal to the negative log of 1.8 times 10 to the negative 5, when I actually do that on my calculator, which I happen to do in advance, I'm going to end up with a pH of 4.74. And that's pretty straightforward. Again, it's a lot easier simply because we're able to get rid of these two X values by the 5% rule. And they give us the same exact amounts here. Now, I'm going to show you something that you're going to like a lot. And it's called the Henderson-Hasselbalch equation. Now, I'm going to camp on this a little bit, but this is a rearrangement of a typical Ka expression. If you took your regular Ka expression, would it not be H plus times A minus? That's excluding the H3O that we normally have in here, HA, and they brought it to this, right? But then when they rearranged it, they ended up with this equation right here, and this is the good stuff. It's called the Henderson-Hasselbalch equation. Henderson-Hasselbalch. I am probably going to spell it Hasselbalch. My students have done a variety of versions of this, the Hufflepuff, Hupsendorf thing, the David Hasselhoff. There's a whole bunch of different ways they've done this, but the nice thing about it is we can plug in values here, and as long as we have both an acid and a conjugate base, we can do the exact same problem we just did without having to worry about plugging in an ice problem at all. So let's say we have this, we have pH is equal to pKa. Now, the pKa value, that's the negative log of the Ka, and I went ahead and did this because the negative log of 1.8 times 10 to the negative 5 is 4.74, and I'm going to add that to the log of my base concentration, which happens to be 0.50. We got that initially, all over my acid concentration, which happens to be 0.50. And I don't want to spoil the fun for you here, but this right here, isn't this the same as log of 1, which happens to be, 0? So what you end up having is this, pH is equal to 4.74 plus 0, which pretty sure is the same thing as saying pH is equal to 4.74. Now, I don't want to rehash stuff, but take a look at the previous problem where we did the whole ice problem. Didn't we get 4.74 by doing all this math here? Now, in this particular problem, because we had the equal amounts of these two, the ice problem and all this became really straightforward. But it becomes even better when these numbers are not the same, because the Henderson-Hasselbalch equation right here, it allows us, if we know our Ka and we know our quantities, our initial quantities, we can plug them in right here without ever having to do an ice problem. So this is something that I want you guys to look through and peruse, and then try it on some of the problems in the book before we meet next class time. Hope this has been helpful. Thanks. Bye.